My name is Simran Kaur, ID number 23607, and today I'll be doing my technical review presentation on reverse time migration. So let's start off with the abstract. So reverse time migration is a seismic imaging technique that uses recorded seismic waveforms to determine subsurface reflectivity. Among the numerous seismic migration techniques for diverse scenarios, RTM is the only approach that can employ all numerically calculated seismic wave types. So RTM, which was founded in the early 1980s, seeks a visual of subsurface reflectivity as the best match in an image space between extrapolation of time reverse wavefront data and forecast based on estimated velocity model and source characteristics. So assessing picture quality in the same space as image formation is more favorable than modeling and inversion procedures. We seek the solution in model space but measures its suitability in data space. So given that the most seismic migration applications still employ primary reflectivity as the main signal, RTM's ability to handle all computable wave types is distinct and useful in eliminating image errors caused by mistaking non-primary waves for primary reflections. So this technical review paper will examine the RTM's development history as well as its primary issues, present solutions, and as well as its future prospects. Moving forward to the introduction. So what is reverse time migration? Reverse time migration is a high-end pre-stacked two-way wave equation migration technique that enables precise imaging in and beneath locations with significant structural and velocity complexity, such as sedimentary areas with steep salts inclusion. So RTM has a track record of successfully providing final visual and is increasingly being utilized to refine structural limits throughout the velocity model construction process. So here this image represents a four-step cartoon showing the reverse time imaging of a source. So the lower part of the panel shows wave propagation in the model space from the star here, which is the source, to the triangle here, the receivers. The upper part of each panel shows the first arrival wave field recorded by the receivers in the X time plot of the data space. So the three left panels here shows the snapshot of forward wave field at time steps T1, T2, and T3. The rightmost panel shows the time reverse data wave field in the X time inverse plot, which is taken as a boundary values to be extrapolated downward in the model space from the receiver, achieve a source image. Next, we'll talk about the literature review. So there are three aspects in the literature review that I will touch on, which is the advantages of RTM in the industry, as well as the limitation of RTM and ways to solve those limitations, as well as the future prospects of using reverse time migration. So first, let's look at the advantages of reverse time migration in the industry. Now let's review a paper done by Farmer, Jones, Zhao, Bloor, and Goodwin in 2006. So standard short-based one-way wave field extrapolation techniques show that the wave fields travel along the direction of extrapolation only in one direction, which is downwards for the source wave field and upwards for the receiver or scattered wave field. In actuality, when the velocity model is complicated, multiples are formed. Furthermore, approximations in extrapolation procedures often restrict the dips in the final picture to less than 70 degrees. So Kirchhoff methods are often used to image steeper dips and twisting rays. However, they fail to provide a satisfactory imagery when we have a multi-parting situation. So then migration utilizing the two-way wave equation is one of the strategy that can handle all of these concerns. To do this, they have employed an anisotropic reverse time migration technique. So RTM successfully propagates the wave field across arbitrary complexity velocity structures, imaging dips bigger than 90 degrees. When the boundaries responsible for the multiples are present, in the model, it has the ability to image with with internal multiples. So here from the image here that we can see figure 1 and figure 2. So figure 1 is a subsalt image generated with the SSFBI one-way WE migration. Shows poor imaging of salt flanks and subsalt structures. And here on the image 2, we can see a subsalt image generated with the RTM technology, which shows significant improvement in the imaging salt flank. Even beneath the salt, there is satisfactory imagery produced. So now let's move forward to the next paper by Totten and Zhao in 2008. It is said that in crustal and mantle seismology, the use of reflection data has generally been confined to common midpoint CMP stacking or post-stack migration procedures. Totten and Zhao argue that the challenges for seismic imaging using crustal reflection data necessitate the use of vigorous imaging methods such as RTM rather than CMP stacking or conventional seismic migration methods in an analysis of 2D crustal reflection imaging using both synthetic and field data. So the figure here shows a comparison of Totten and Zhao's paper between the results using three different seismic imaging methods to the same reflection data. So with respect to the CMP envelope stack and post-stack depth migration results in panel A and panel B, respectively, the RTM image in panel C shows much more coherent reflection events, including some strong reflections below 25 kilometer in depth that are compatible, which is below here, below this 25 in this area. So the preceding comparison analysis shows that the wave-field correlation step is a highly useful tool for RTM to differentiate between the intended reflection and other noise events in the recorded wave field. Furthermore, since RTM is a modeling technique, each frequency component may be photographed individually, enabling the final image bandwidth to be estimated after the events have been positioned and stacked. Because the fundamental problem with crustal reflection surveys is low signal to noise ratios. The influence of wave field correlation and the ability to choose bandwidth after imaging is crucial for enhancing the picture quality. So now let's move on to the limitation of using reverse time migrations and ways to improve those limitations. So on the limitation part, we will be looking at the paper done by Yoon in 2004. Says that RTM should ideally link the calculated source wave field with the extrapolated receiver wave field to provide a reflectivity picture. So RTM can detect stiff interfaces without a deep constraint thanks to the inclusion of the two-way wave equation. However, if there is a high velocity difference such as a salt body, the two-way wave equation yields inverted energy as well. So the interaction of these raised waves, plunging waves and head waves produces visual distortion, particularly at shallow depths. So the ways to improve this, so the methods for reducing this RTM imaging artifacts may be classified into three types. So the first method is to mute or filter the input data. The second method is to filter the migrated traces before generating the final image. And the third method is to filter the final migrated picture. So the first strategy is successful if a relationship can be established between the components of the input data and the image artifact. So the muting of low slope head waves and turning waves at a large offset is one example. So moving to the next limitation, we'll be reviewing a paper done by Huawei, Hao, Zoe, Yukai, and Ong in 2018, which says that because the second generation RTM involves solving the two-way wave equation, which normally necessitates a large amount of computing, its users have been hampered in past due to high computational time and expense, because the time domain ICs of pre-stack RTM need both the forward propagated source wave field and the backward propagated receiver's wave field to be accessible concurrently over the whole imaging time frame. A massive quantity of computer storage of the wave field is required. As a result, boosting computing efficiency becomes one of the primary obstacles for implementing RTM in the industry. While various research have been conducted in the previous 30 years to improve the computational efficiency of RTM, they have consolidated the techniques into four different categories. First being optimization of wave field propagators. Second, replacement of wave field storage. Third, reduction of data redundancy. And lastly, hardware acceleration. Now let's move forward into the future development. So, paper done by Huawei, Hao, Zoe, Yuka, and Ong in 2018 states that the second generation and improved RTM techniques could give more accurate and trustworthy subsurface pictures in solid earth geophysics, exploratory geophysics, and near-surface geosciences, employing diverse forms of seismic waves as signal, including multiple reflections and converted waves. The capacity to detect the nature and origin of wave types in data is one of the most difficult tasks in seismic imaging. Enablement to utilize each wave type as signal rather than noise will assist. The goal is to identify suitable wave types from data field. So that concludes my presentation. So we have highlighted the concepts of reverse time migration in mapping subsurface reflectivity structures, as well as the main difficulties and solution options. RTM is the only seismic migration technique that can employ all computable seismic wave types as signal in mapping the subsurface by numerically propagating seismic wave fields from seismic sources and receivers in an image space. Thank you and a good day to everyone.